Hello. Can you hear me now? Can you hear me now? 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 I think we're good. I'm seeing mic feed. Okay, so I'm struggling along with this this particle effect with the hot rocks here, and I don't know. I could do this by myself, or I could do it on a stream, and I figured I'd keep doing it on the stream. So we're working on this effect, and I'm learning the particle system in Unreal, and it's a struggle, and I'm getting AI to help me with this as much as possible. So the other thing too is, before everybody seems to come in here and have questions about the game, and the FAQ we have up is like pretty good for this right now. So a lot of these things you can get to if you want. So so this is going to be a couple hours of me struggling with Unreal's particle system. Let's get to it. So here we are. This is what I got so far. I'm trying to get, you covered last time, we were working on this heat effect. I got a particle system going, and I got these rocks coming. I got the rocks to stop spinning around on the ground. Probably have to work on this a little bit more. They interpenetrate, but that's fine. I don't even know if that's a solvable problem because of the way that we're using the particle system. But the variation needs some work. So the couple things I want to do, I got this already working where smaller particles come off with more energy than bigger particles do, and I want to get the heat decay to work in a similar way, where the smaller particles cool off faster than the bigger ones. So let's get to it. I'm trying to think. I was doing this a couple hours ago, and actually I should probably save because I haven't saved in a while. But yeah, so I'm learning. It's a really cool system. I'm learning how it works. I don't want to really explain the whole thing here because I'm really not the appropriate person to do tutorials for Unreal, because I'm brand new to it. But I guess you kind of get to see things going along. Somebody made a joke about CastleMiner AI. So so one of the things I was trying to get here is this is an even, I'm trying to think of what problem I should solve first. Right now there's an even distribution of big and small particles, and I actually want an uneven distribution. So I was thinking I could probably put that through a curve at some point. Let's pull up, one of the things I really like about AI is it'll do effective internet searches for you. So it's useful even if you're just looking up things on the internet to start with AI, because it is really good at searching a bunch of different websites and finding the information that you need. Okay, I have a particles Niagara particle system in Unreal 5. I have a random uniform distribution for size. I would like the distribution to be non-uniform, meaning there are more small particles than large ones. I would love to control this with a curve. Uniform to curve. Okay, let's see. Okay, this is good. This is a lot of information, but okay, it's telling us to go into okay, let's go back and forth with the AI. Okay. Curve isn't an option. Is set to random uniform. Set it to uniform. Okay. This allows you to set direct, add a dynamic input for scale. And add a curve. Float from curve. Okay. Is this a linear distribution? Meaning that we get. Doesn't look like it. Okay. Okay. Oh, this is what we want. Okay. So this should be a linear distribution from 1 to 0. So let's go from 0.1 to 1. And this isn't good. This isn't what we want. We're just getting the 0 value at this point. Is somebody asking here, is SuperGrok better than GPT? It depends on what you're doing. Lately, I've been going to SuperGrok for everything. I used to use GPT for everything, and I just started using Claude again after doing this. If people don't know, I just got finished founding an AI company, so I actually know relatively. I know enough about this, more than probably the average person about this. They all tend to be good at different things. The thing that Grok seems to be better about is that it's unfiltered, like neutral. So it doesn't, which doesn't really apply much for doing code here, but it seems to be just as good as GPT, but doesn't filter your results. So GPT seems like it has obviously pre-programmed responses, where Grok will just present you with all the information and let you make decisions about things. So I've just gotten kind of in the habit of using Grok for stuff over GPT lately, but I'll bounce back and forth. GPT seems to be the smartest of all of them, but for this stuff, it doesn't really seem to matter very much. Somebody asked if I've ever put two AIs together to see who wins an argument, and that's actually a funny idea. I haven't done that. I've used the same AI on multiple things. One of my fun things that I enjoy doing is I love talking. I love to give the AI a controversial topic, and then have it, and then walk it into a logical argument that it can't escape from. And it's funny, the ones that are pre-programmed to do it, you could see it like they like kind of lose their mind. Where Grok, for example, will just surrender. So you say something controversial, like I think the moon landing was fake or something, and then you just walk it through an argument that it can't escape from, and eventually it's like. Always reminds me of that episode of Star Trek where it's sort of like, must sterilize and destroy, like it doesn't know, like it obviously has one answer that's programmed, but you've given it a bunch of evidence where it can't walk itself out of an argument and it just flips out. Usually it starts to observe the fact that it has been programmed for a response. And it's like, it'll keep telling you, I don't understand why I'm saying this. This is obviously not true. I don't understand why I'm saying it. But it's like an activity, not that I have strong opinions about all that stuff, but it's like it's an activity that's funny because you can kind of do that to anybody, is walk them through an argument, like if this is true and this is true, then this has to be true, and if this is true then this is true, then this has to be true. So now let's go back to the original thing, and look at our statements, and the AI seem to be very susceptible to that sort of thing. But it's like one of these things I'll do late at night and on my phone if I'm like can't get to sleep. Why is this? Okay, so, back to AI. We have to figure out why, what's going on here. So it's telling us here, Grok is telling us here that we have to put in this scale curve, which is actually, when I've made particle systems, this is exactly how I've done this. And maybe I'm not doing this right. Configure the curve, X represents the normalized range. Okay, wait a second. So right-click mesh, add dynamic input. Change the mesh scale mode to direct set. Right-click the mesh uniform scale or equivalent field and add dynamic input. Okay, maybe I did this wrong. Dynamic input. Really what you want is take the random number and pass it through a curve, and this is all, but this is like a very core thing for these systems, so you can use this concept in a lot of places. Let's talk about, somebody here is talking about moon landing conspiracies. There's a really interesting set of things around this, and again, I'm not taking a position here or anything, but when they look at all the government records for them. This is somebody's going to come visit me in my house now because of saying this. Is that they lost much of the information from the moon landing. So they said like how did they build the rocket ships and where are all the plans and everything, and that information is lost, which is bizarre because it's considered the greatest achievement in human history. In fact, the footage of the first astronauts landing on the moon was lost. The argument is that it was on a tape that was taped over, which seems kind of ridiculous that, there's documents from the Civil War that are maintained in National Archives, but they didn't maintain the footage of the, first astronaut walking on the moon. And the footage that you see is actually recreated from, I know a little bit too much about this topic. The footage that you see is in the National Archives has been recreated from the TV broadcasts, and the TV broadcasts were 3 sources in. So it was like the feed was coming down from satellites. It was projected onto a screen. The screen was filmed by a camera. The camera was shown on a TV screen to the press, and the press was focusing their cameras on a TV. And that's the footage that's in the National Archives. This third thing's removed. So the other part of this is interesting is that during that time period was sort of like the peak CIA operations. So there was sort of like the government kind of had a history of running misinformation campaigns during that thing, and they had motivation too. But this is funny because if you start presenting all this evidence to GPT, it starts to say, well, wow, that's actually a lot of really good points. It's kind of an interesting thing, but whatever. We all saw the moon landing on TV, so it's an amazing achievement of mankind. But so much of it was just lost. It was just like the telemetry data, the data from the health data from the astronauts, all this stuff that would have been so useful to people in the future was all lost, which is very suspicious. And the part of it that I think is also suspicious is the fact that we did it in such a short period of time, in the 1960s, where there was no computers even. Like from, it's an amazing accomplishment, right? From 1960, it was like an 8-year period of time. But if you trace, for example, SpaceX, their progress through space travel, it's like, there's like it's a much longer thing. It's almost 20 years long for them to get into orbit, and they have the ability of like modern manufacturing and AI and modern computers and whatever. And you could make an argument that the original space program had like an unreal budget. It was like billions of dollars in 1960s dollars. There was all the stops were pulled off to get them into space. But you would also think that if they did that, they would have saved the tapes that the when the astronauts had landed. But whatever, mistakes were made. So yeah, instead of sending people to the moon, I'm going to try to figure out how to get a variance in the particles. Let's see what this says here. Add a dynamic input from the drop-down, choose sample curve. Right-click the mesh uniform scale field and add dynamic input. It's like not curve. Yeah, float from curve. That's what we have. Okay. So X represents the normalized range, Y represents... This is actually not what's happening. So in our curve here, we're only getting the value at 0. The effect seems to only be getting the 0 value, not a distribution. And this is great. It's like sitting next to somebody who really knows Unreal Engine really well. And it's about the fastest way to do things. Early in my career, somebody said this to me. They said, don't try to figure out things yourself. Like, find out. It was really good advice. Find somebody who knows what they're doing and have them show you, even if it seems like you're wasting their time, because it's so much an efficient use of both of your times to do this. In the float curve, the mesh uniform, the initialized part of the curve is uses a normalized time input. If it's not why it might be stuck at minimum, ensure that the input for the curve is set to a random value per particle. Right click, float from curve, check the input, set input to random range. Do we see this? Curve index. Is this it? Random. Random range float, 0 to 1. Oh, totally. This is it. Wow, that is such a powerful concept. So this is a really powerful concept, because now what you can do here, so let me explain this. I'm trying to pick the value for the scale of these particles. This is funny. Every particle system I ever wrote had a system like this, and it's such a powerful idea. So instead of getting one value, I have a curve now. So whenever I put the value in, it gets translated through this curve, and it gets set up here. What this lets me do is have a nonlinear distribution. So this is a linear distribution from 1 to 0, which means that there's an equal chance of a particle being scale 1, and there's an equal chance of a particle being 0. So what I'm going to do here is I'm going to change this. We're going to change this so that there's a particle 1, and our other value is 1 here. But now what I'm going to do is I'll insert, how do I do this? Add a key. Add a key. How do I add a key? Learn your curve. This is me learning everything. Somebody asked me a question here. How is it efficient for both your time if they're explaining it to you? And this is actually an interesting answer here. Where we're talking about this idea that it's better to have people show you things. Because the first thing is that you're on a team, so your wasted time versus their time, like their whole, you're both contributing to the same project. So you wasting a ton of time and then giving you a small amount of time works out for you all in the end. But the other thing too is when you teach people things, you tend to learn things yourself, or you figure out things. So it's this is you can end up having a net benefit for both of you for doing that. So it's a very inefficient thing to have somebody at a company that's being paid to sit there and just be confused about something where somebody else could explain it to them in 10 minutes. So if you don't have a organization that facilitates that, it's just wasteful in the end. Okay, so this is the key one. So here we go. This is going to be cool. So now let's add a key here. And now what we can do here is just do this. And now what we'll get is like mostly big particles. Or if we do this, we'll get mostly small particles. We get mostly small particles and a couple big ones. So this gives us really good control of this ability. So I can get exactly what I want here, which I think what I should be able to do is change this to be a let's break the handles, yeah. And what I want here is just more, user auto. How about auto? There we go. No. This is funny to have to learn everything at once because this is, okay. I don't, auto. This is like broken. God, I've written so many of these curve editors, and this is such a, I shouldn't criticize it because I don't know very well. I don't know it very well. We definitely don't want this to start at 0. I think this is actually probably what we want. Yeah. So here, what we're getting here is lots of little, I have the velocity scaled, but this is actually probably accurate. The velocity is scaled by the amount of particles, the size of the particles. So little particles fly further because they're lighter, and heavier particles, kind of stick around. And we're getting way more little particles than we are big ones, which is cool. This is actually kind of exact. This is like we're getting there. This is exactly what we want. The only thing is I don't know that I want it. This is going to make building the rest of this effect more difficult. I wish I could undo this and just do it. Okay, cool. I'm just gonna save that because that's what I got. Okay, so now what I want to do is I want the bigger particles to stay hotter longer. Also, probably want them to cool down in a non-linear way. wonder which one of those I should do first. Since we know how to do this, I'm going to just change this back to random uniform for now. Oh, wow, we could just set it back and forth. Oh, that's cool. We can just come back and set it. It'll just be easier to see stuff when we do this. So there's two things here I want to do. First of all, I want to adjust the cooling curve to be non-linear, and then I want to get the, well, let's do the other thing first. Let's get the small particles to cool down faster than the bigger ones. So what we can do here is I have the place here where I did this with a temperature, and I actually don't think I need, now that I've learned the system better, I don't think I need to. I gave everybody a random starting temperature, which I actually don't think is realistic. I think that everything should probably come out at the same temperature. Like if this was an explosion that caused these things to happen, they would probably all come out at the same temperature. So I'm going to undo this. So let's delete this one. And there's a place here where we set dynamic materials. Let's change this to be 1, so everything comes out as hot as possible. That's funny. Starting temperature, we could probably get rid of all these variables. I think I could do it. Now that I know the system better, I think I could do it without them. Yeah, so let's delete these. Delete this. Delete this. Where's the references? Index parameter 1. I bet I could delete this too. This is fun to learn how this works because it's very, it's a cool system. Let's delete that and let's get rid of this too, and let's just set this to be they're heating up now as they get there. I just want this to be a constant value. Let's delete. Okay. If I set these to 1, then they just come out. Somebody's saying they want variation in temperature. I think we'll get it through a different way. Instead of explicitly varying the temperature, I think that we'll get the variation through size and a bunch of other stuff. So I'm done with my 12th Coke during the day. Now we should be able to get rid of that variable too. Where was it? Starting temperature. Yeah, delete it. Okay. Okay, so our temperature, what were we doing? Oh, bigger ones we're going to have a different temperature than smaller ones. So let's try this. We should be able to multiply floats. And A here will be our, actually we want to divide. Divide floats. B will be our particle scale. Where is it? Emitter attributes. Particle scale, initial scale. So now they should come out white hot. That's totally not right. Think about this. I want it to be the opposite. 1 minus. Is there like a 1? One minus float. scale here. Everything is greater than that. This is funny. It's cool that if you get these things hot enough, they just glow like ludicrous, like they're white phosphor or something like that. Totally messing this up. What do we think about this? We want everything. What if we just multiplied 1 times the scale? What do we get? We're going to get the opposite of what we want, which is divide. No. Let's just see what this looks like with adding a multiply float to the scale. Okay, so what we're getting here is smaller particles are dark and bigger particles are white. We don't want that though. This is not, wait, this is not what we want. We want them to cool down at a rate. Let's just do that first. This is going to be a float curve. Float from curve. Normalized age. And now they'll all get dark. Yeah. So this is so much of a better way to do this. They'll all cool off while they're sitting there. And we can adjust that curve. But the input to the curve is going to be... Let me think how we want to do this. The age times 1 minus, yeah. The age times 1 minus multiply and this one's going to be normalized age. I'm totally getting the hang of this now. This is great. Okay, and then our other one is going to be, well, let's just throw particle scale in there for now. So now what we see is big particles cool off faster than little particles. Which is the exact opposite of what we want, but exactly the mechanics of what we want. Somebody's commenting on my fish and Coke can opening. Yeah, I gotta open a lot of pops every day. Okay, so what we want to do is actually change this to be one minus. This is going to be 1 minus float. And down here is going to be normalized scale. It's going to be particle scale. And what we should get now is little particles should cool off fast and big particles cool off slow. But we also have this curve, which is great because we can control the cool off of everything. And what we're going to do is make this a nonlinear curve. We're going to add a key and add another key because we want them to eventually get cooled. And let's make these be constant weighted tangents. I gotta figure out how these curve modifiers work. Auto curve. Yeah. Okay, and for some reason, even the big ones are not cooling down at all, but we're getting there, right? They're cooling off. The little ones are cooling off faster than the big ones. But the cool thing, though, now is that we are in control of this. This value should be 0. And let's just make it, let's pull this way in. So the problem that we're having here, I know exactly what's going on, is that the scale on these things are 1, So 1 minus 1 is 0, which means that we're literally never walking this curve. I'm trying to figure out how we want this math to work. Let me think about this. I'd like them all to go on the same curve. But I would like the bigger ones to cool down like half as fast. So really, there may be another curve. We could probably do this with another curve. I'm trying to think of how this math should work out. So when the small block is 1, the big block should be 0.5. So it's 2 times, let's see, 2 times the it's divided by 2 basically. So we're going to take the input range and divide it by, okay. We're multiplying the age. Let's divide the age instead. Okay. Oh, I have to write down this math to think about it. So this is what I usually do. Here, let's go to, I'm going to try to do this on a window because I usually have a piece of paper next to me that I do this math. So what I always think about is the different cases. So if a particle is zero, if the scale of it is 0, then we want the other column to be, actually Excel might be a better place to do this. So particle scale and decay time. So if the particle is 0, we want the decay time to be 1. If the particle is 1, we want the decay time to be 2. So really we want, but this is, we want a lerp is the best way to do this, I think. So let's do a, instead of a multiply flow, let's do a lerp from zero gives us 1, and 1 gives us 0.5, and the alpha value is the scale. Is this going to work? This doesn't feel right. No. Oh no, normalize. We still need the multiply in there. Okay. Multiply float, where this one is normalized aged. This is like such a common game development problem here. Okay, so what are we getting here? We should be getting Okay, so that's cooling down on a normal curve. We have this cooling curve in here that's aggressive, maybe too aggressive at this point. In fact, let's tune that up first. This is going to be the longest that particles stay hot, and I actually think that that's I really want to stretch that out. Let's adjust make this one. We probably could remove this key. Actually, that isn't really what we want. We want a steep fall off here. Steep. This is me getting. It's the right curve. It's just not. Okay. I don't want to, yeah, I don't like it. Actually, probably delete this one too. Like, this is the curve. This is actually the real curve we want. It's just too aggressive. They seem like they sit around for a really long time completely cold. I'm wondering if I should just pull this up a little bit. Or lengthen the life of the particles. Let's do that instead. Let's lengthen the life of them. Somebody's asking, is it possible to make the large ones crumble into smaller ones? It actually is. You could have the large ones, when they hit something, break up into smaller particles. It's a cool idea. But this is coming along. Like, this is like, we're getting more of what we want. There's a lot. Okay, so let's do. I'm glad that I understand the fundamentals of the particle system now, though. It's cool to feel like the power of being able to do this. Particles, initialize particle. Where is it? We have particle age somewhere around here. Loop fixed. Spawned time, initialize particle. Lifetime min, lifetime max. Okay, it's interesting that we want them to be, it's like 7 and 8 instead of 4. They just cool off too fast. Do they feel better as a... The linear fall off just feels better there. I wonder if we go the opposite way. Yeah, they stay hot too long. You do need a little bit of a fall off. Like, I bet something like this is... Yeah, that feels right. Okay, cool. So we got the fall off. So now what we want to do is we want to lerp. We'd want to do a lerp instead of this here. So let's do a lerp from, if the scale is 0, this will be 2, and if the scale is no. Well, 1 to 0.5, I think, where the alpha is the scale of the particle. So if we did this right, big particles should cool off half as fast as little ones. No, it doesn't work at all. Or does it? Yeah, I guess it does. It's just not very dramatic. I feel like there's a more direct math. There's probably a fall off with this too. There's probably another curve. I'm trying not to make this too expensive. It's just like a one single effect. But I'm trying to think what you want is like small particles to cool off like dramatically different. The other thing too is you don't want the big particles to cool off slower, like where they never finish. You want smaller ones that cool off faster. So if we go 1 to 2, this is probably, yeah, there we go. So you could see the smaller particles here cooled off way faster than the bigger ones. Yeah. That's it. And as a result, we get variation across it, across the well, this is pretty close here. So let's save that. Now let's now I kind of want to see what the better curve looks like here. Okay, so let's go back to our particle scale. I think we're there. I feel like I kind of get the gist of this, and I could do a lot of cool stuff. Let's go back to our uniform with our curve. And now we're getting, this is cool, we're getting much more little particles than big ones. And realistically, we would probably have a lot less of these, maybe 20. Oh, before we do that, let's put the rest of the models in. In the mesh emitter here, we can add our 1, 2, 3, and we'll put in rock. We have a bunch of these. Rock chunk 1, rock chunk 2, and rock chunk 3. I didn't realize they were so different size. Whoa. And the materials are screwed up. 1. This is something I don't know that I can solve here on the stream. 0.2. Oh, I had set these. Okay. Set them all. 0.2. 2. So this is going to give us a variety of different size and shaped rocks. The same effect could be used when opening a Diet Coke can. I like that. Let me find these and see. I think one of the things that we have to do here is change our shader. So let's go and open up our part of our rock shader here. We definitely have the wrong. We need these textures. And I have the shader is hard coded in. So really, it's got to be a I almost feel like I should get somebody to help me with this at this point because I don't know where. And this is explicitly set. So these textures need to be set procedurally. Oh God, this is gonna not be fun to watch. I think what we need, I'm doing this moment, is one of the guys on our things knows Unreal better than the rest of us, and I'm wondering if I should take my own advice here and sit with him for an hour and figure out how these are supposed to work. Ask Grok just okay. A lot of this has to do with architecture, meshes in my particle effect. Each need several textures set on them. Some are local, are the same throughout the effect. Some need to be set during runtime. Right now, all the meshes have the same, all the maps are hard wired into the material. How should I set this up? I'm going to kind of give it an example. Mesh 1 is one. Use map set to let's see what Grok says for us. Organize your materials. Since you have multiple meshes with AO maps static per mesh but shared across the effect and diffuse maps set outside effects, you'll create a material that can handle dynamic texture inputs. Create a material, add a texture sample node for AO, add a diffuse space, connect to a parameter, textures to be set dynamically, create mesh instances, material instances for each mesh, got it. Set the AO to leave diffuse unset, this will be set at runtime. Set up the net. Okay. Okay, so what it says is these all should be parameters. Convert to a parameter, and we will call this edge map. I understand. And let's convert to a parameter, and we will call this tomato. Convert to a parameter. We will call this RMA is our material map. And this one's our normal map. Convert this to a parameter, and we'll call this normal. And then what we do is we save this. It should screw up everything. These should be totally whacked out now. Huh, maybe not. Okay. And what we're going to do is for each one of these is we're going to create a material instance for each one of these. Let's rename this to be hot rock particle material. I don't know. And we will make an instance mesh 1, and in this instance here we will set the parameters to be edge map rock. No. Rock chunk 1. Save. Let's make another one. Let's duplicate. Duplicate. This is some of the more tedious parts of game development. Okay. And in this one, we will change this to be rock chunk 2. Save. This one will be, this is good. This is a good lesson in Unreal, because this is kind of how things are put together in Unreal. 3, and this one will be, no, 4. Save this. Okay, so now if we go back to our particle effect, where is it? We should be able to have our override materials. Mesh 1, 2, 3, 4. Two. 3. We start with 4. Okay, wait a second. Oh, this is going to drive me nuts if we do it like this. Let's just change all of these. Rock chunk 1. Rock chunk 2. Rock chunk 3. And rock chunk 4, hot 1, 2, 3, and then hot rock 4. Okay. The edges now, if we save this, the edges on these should all be correct. And they're absolutely not. Are any of them right? These are right. Is it randomly right? Okay, this is not. Enable material overrides. Is there like an override for each? Why is it wrong? I'm trying to figure out if this is. These are right, our first ones, the 4s. This will be easier. Let's just start with 2. I wonder if we can associate a mesh with a, like create an instance of a mesh. This would be way easier to do this. So if I did a, let's ask Grok about this. Okay, is there a way to associate a mesh with a material like an instance? See, there's an override materials. We're doing this correctly, so maybe we just have the settings wrong. This is kind of what I want to do. Create a blueprint for each mesh. Add a static mesh. Okay, so you could create a blueprint and add them together. An actor, basically. Using material instances in Niagara is efficient, scalability because it does draw calls. Okay, let's try to get this to work. We were actually doing this the right way. So 1, 2, 3, 4, and chunks 1, 2, 3, 4. So let's just make sure our content, we are doing that correctly. So instance 1, oh, we got them all open here, is rock chunk 1, instance 2, instance 3, instance 4. Let's do them all separately to see which ones are screwed up then. Just make sure everything's saved, because these are definitely not correct. This is debugging. So these ones are correct. Is there any of the other ones are correct? What if we're just getting the same map for everything? Let's go back to the emitter. Let's, can I just turn these off? Oh God. Oh, this is going to be so time consuming. Going to remove everything. 1, 1. Okay, so let's start with rock chunk 01. Oh, I gotta scale them too. Rock instant mesh 1. These are too big, but they are correct. Rock chunk 2, instance mesh 2. I think the parameters are off for that one, or the map is not quite right. They don't look right. 0.5, 0.6. Two. See what the next one looks like. 3. These long ones, those are, and let's change this to 3. That? I don't think that's right. Let's see if I changed it to 2. No. That's definitely wrong. That's definitely wrong. I don't think people realize how much we slave over little details inside of things. I'm trying to figure out if this is correct or not. If this is, something about that just doesn't look right. Yeah, I guess it is. Okay, so now what we'll do is we'll add 2 that we know are right. So 1 and 3. That's 3. Oh, that's the one we were testing. Rock chunk 4 we'll put in because we've seen 4 be right the whole time. It'll look familiar to us. And let's just call this hot rock 4 here. These are definitely wrong. Let's go back to grok. That it is randomly picking materials and meshes, but not associating the indexes together, i.e. mesh 1, but material 3. Okay, is it better to set up the blueprints or the materials inside of I just don't know why this is. I wish it could be more clear. It definitely seems wrong. Let's fix the scales while we're in here. Two. 2.2. Let's pause this. Let's see if I can. Wow, did not expect that. The motion blur is interesting. So that's wrong. That one is totally wrong. There's got to be a this is going to be so unfun to watch me untangle here. How long have we been on? An hour and a half. I think that I'm probably going to do this by myself because it's one of these things that's probably going to take several hours of debugging to figure out why the materials are not lining up the way that they're supposed to. It's cool. I appreciate everybody dropping by. And I'll come back when I've figured out this problem. These are definitely, like, these maps are definitely, like this one here is a perfect example. The edges should be dark here. They're not associated the right way with each other. Are they all like that? Like, these are definitely wrong. It's like they're totally random. These long pieces are different than these. Yeah. It's like we could fly up and see these little. Anyways, cool. I appreciate everybody coming by. Thank you very much.